Okay, for topic 3, we're going to look at converting polar coordinates into rectangular coordinates. Okay, so rectangular coordinates are the regular XY coordinates that we're used to, those nice normal ordered pairs. You have your X coordinate, then you have your Y coordinate. So we're going to go from this idea of R comma theta to X comma Y. Okay, so let's think of it like this. Let me go to, we have R and theta, but we need X and Y. Well, how in the tarnation do we go from R theta to XY? It's actually quite easy. So let's kind of go back to this idea of the rectangular coordinate system. And remember, like eons ago, it feels like when we were back in chapter 7, and then again really in chapter 9, we did a lot with those right triangles. Okay, so we have our x-axis, we have our y-axis, we have the regular old origin, and we could build some angle. So let's do this kind of in red just to make sure everybody can see. So we have the terminal side or the initial side of our angle. We sweep it open some value for theta, and then we have the terminal side, and on that terminal side we have some point. So we have some point P. Well, if we drop down a line from that point P directly to the x-axis, we create a right triangle. And that's really, really cool. So this base, this distance right here is just some x value. This vertical that we drop down is really just some y value. And then we obviously have some angle theta that we measured. And then let's not forget, we have the distance from the origin to that point. We called it r. Okay? And so we go back to this idea of right triangle trigonometry. What do we know about, well, sine and cosine in particular? We like sine and cosine because on the unit circle, remember those ordered pairs that were on the unit circle? They had the cosine and then they had the sine. So like x was cosine and y was sine. So we end up using lots of sines and cosines. But let's just use the sine and cosine here because they're really powerful. Okay, if you have some angle theta, okay, sine of theta is always going to be equal to the ratio of the side opposite theta divided by the hypotenuse. So in this little situation, the side that is opposite theta is y, and the hypotenuse, we've labeled it r. So we have that sine of theta equals y over r. Well, for cosine of theta, let me scoot it down a little bit so I have more room. For cosine of theta, we know that cosine of theta relates the side that is adjacent to the angle, so the side that touches theta, compared to the hypotenuse. So for this situation, theta is touching this side x, that's the side adjacent to theta, and we're going to divide it by our hypotenuse, which we have very conveniently labeled r. Okay, so we already know this right here. We know from our worlds ago lives that we had back in chapter 7. Okay, we know from right triangle trigonometry, if we have some angle that we've drawn, we find a point on the terminal side, we drop down a vertical line directly to the x-axis, we create some kind of a right triangle, and we can look at the sine and cosine of this angle, and we can get that sine of theta is the ratio y over r, and cosine of theta is the ratio x over r. And we really like this in the unit circle because in the unit circle, r was always 1. Okay, so that's what made this so nice. But for us, we have our y over r, we have our x over r. Well, let's say we take this y over r, so sine of theta equals y over r, and let's solve it for y. Okay, so if I have sine of theta equals y over r, and I want to solve it for y, I would need to do something with that r. So I can multiply both sides of this equation by r. On the right-hand side, the r's just divide out. And what am I left with? Well, I'm left with y equals r times sine of theta. Well, that's super handy, right? Because in the current world that we're living in with polar coordinates, we have a value for r and we have a value for theta. So if we can plug r and theta into this, we can get a y coordinate, which is just unbelievable to me. This is like so cool, right? Now, on the same note, if we do the same thing with cosine, we have, well, cosine of theta equals x over r. Let's solve for x. To do that, we multiply both sides by r. Well, on the right-hand side, the r's just divide out, and I am left with x equals r times cosine of theta. And the great news is, in a polar coordinate, we have a value for r and we have a value for theta. So if we can plug r and theta into this right here, we can get an x coordinate. So that's how we convert from polar coordinates back to rectangular coordinates or into the world we know. So please keep this in mind. That is exactly how we're going to convert from polar to rectangular. Okay, so let's go ahead and practice. I have quite a few practice problems for us. I think 6 total. 4 of them are very reasonable. 2 of them are a little bit wacky just for, they keep you honest. They make you like stretch your brain a little bit. Okay, so when you're converting from polar to rectangular, I do ask that you always make note what quadrant is my polar coordinate in. Because wherever your polar point lives, your rectangular point needs to live in that exact same quadrant, okay? So be very mindful of which quadrant each point lives in. They need to match. They need to be in the same quadrant, okay? So example 3 here says, find the rectangular coordinates for each polar coordinate point below, okay? So let's first imagine where 5 comma pi over 4 is. So if we have pi over 4, that would be approximately that angle. So we would sweep open our angle, and then r is positive, so we would go out 1, 2, 3, 4, 5 units, and we would have our polar coordinate point here. Okay, here being which quadrant? Well, this is quadrant 1. So we want to make sure that when we convert this to the rectangular form, that point is also in quadrant 1 because these represent the same thing. We're converting from one form, polar coordinates, to an equivalent form, rectangular coordinates. So they represent the same spot. We're just representing them in 2 different formats, but they represent the same location in space. Okay? So let's look at our x. So let's figure out our x coordinates. So remember, x coordinate is r cosine of theta. Well, r is 5, so we want 5 times cosine of theta, where theta is pi over 4. So we get 5 times, well, this is where the unit circle is. She's back. She's back again. Okay, y'all. So what is cosine of pi over 4? Well, cosine of pi over 4 is root 2 over 2. So this would just be 5 square root 2 over 2. That is our x, okay? Now we want to do the exact same thing, but for y, okay? So y, you have to remember, is r sine theta. So it's going to be 5 times sine of theta, which is pi over 4. So it's going to be 5 times, well, again, where's that unit circle? Pull it out if you still need to look at it. What is sine of pi over 4? Well, sine of pi over 4 is also root 2 over 2. So we get 5 root 2 over 2. So my polar, well, not my polar, my rectangular point, whoopsie. There we go. So my rectangular point is going to be 5 root 2 over 2, comma 5 root 2 over 2. Well, is this still in quadrant 1? Yes. If your x coordinate and your y coordinate are positive, you are in quadrant 1. I was about to spell it out. I don't have room to spell it out. So we are still in quadrant 1, and this is our rectangular coordinates for that same exact point. Let me outline it maybe in red. So there you have it. It's not terribly difficult. Now, plotting this rectangular point would be kind of nasty because let's see what this ordered pair would be. 5 times root 2 divided by 2 would be like 3.5-ish. Okay, so we would have to measure out 3.5 along the x-axis, then up 3.5-ish. Okay, so you'd have to definitely do some rounding and estimating with these points, but that is the rectangular point. That's your xy coordinate. Okay, so let's do the same for point B. Okay, so in B we have -2 comma 5 pi over 6. So let's think about where this angle lives. Okay. Now, 5 pi over 6 is way over here. Okay, so this is 5 pi over 6. All right, but r is negative. So we don't want to measure out r along the terminal side of this angle. Instead, we want to measure out r in the opposite direction. So we would measure out 2 units in the opposite direction. So this point is actually in quadrant 4, okay? So this is in quadrant, you can do the Roman numeral. I'm just going to do the regular one. So this is in quadrant 4. So when we convert this to its rectangular form, it needs to be a point in quadrant 4. Okay? So let's do this. Let's look for our x. So remember, x is r cosine theta. So it's going to be -2 times cosine of 5 pi over 6. So you really need to be familiar with that unit circle. If it's still a little fuzzy for you, get it out. Practice filling it in. Okay? If you need a blank one to practice on, let me know. Okay, so 5 pi over 6 cosine is equal to -√3 over 2. Okay, so 5 pi over 6 cosine is -√3 over 2. So we get -2 times -√3 over 2, which is going to be the point just +√3. So when I multiply two negatives, I get a positive, and then the 2's end up dividing out. So we just get positive root, don't put a 2, put a 3, +√3. Okay, so that's our x. Let's figure out our y. Okay, now y is r times sine of theta. So -2 times sine of 5 pi over 6. And at 5 pi over 6, get a unit circle out. In the 7.6 notes, the very first page is unit circle. Again, if you want a spare one, just let me know and I'll get you a spare one. Okay, now sine of 5 pi over 6 is +1/2. So we get -2 times 1/2. Well, 2 times a half is just 1, but then a positive and a negative is negative. So we get the rectangular point √3 over -1. So this is our rectangular point. And let's make sure that this really is in quadrant 4. So the x-coordinate tells us to go along the x-axis, +√3, which +√3 is about 1.7-ish, 1.73. So you're going to go along the x-axis in the right direction. So in the positive direction, 1.73, then you're going to drop down -1. That is definitely in quadrant 4. So we're good. Okay. Now for part C, we have -3, -pi over 3. So let's think about where this point lives. Okay. So if we were at -pi over 3, that would be down here. Okay, so that's -pi over 3. Okay, now our R value is negative, so we don't want to measure out 3 units on the terminal side. We want to go on the side opposite. 1, 2, 3. So we end up over here. Well, shoot. So we end up over here in quadrant 2. So this polar coordinate would be in quadrant 2 for us. Okay, so now let's do our conversion. So x, remember, is r cosine theta, and I am writing out r cosine theta every single time on purpose because the more you write it out, the more committed to memory it is. And remember, the math department really wants you memorizing stuff, okay? So we get r cosine theta, which is -3 times cosine of -pi over 3. Well, at -pi over 3, cosine is equal to +1/2. So get out your unit circle from the positive x-axis, drop down -pi over 3. So cosine of -pi over 3 is going to be +1/2. So we get -3 times +1/2, which is -3 over 2. Okay, now let's look at y. Y is r times sine of theta. So -3 times sine of -pi over 3. So again, at -pi over 3, sine is going to be -√3 over 2. So we get -3 times -√3 over 2. So that's going to be +3√3 over 2. And let's draw out our ordered pair. So we get -3 over 2, comma, 3√3 over 2. So the first point, the x coordinate tells us to go in the negative direction on x and then up. So that for sure puts us in quadrant 2. So this is our rectangular point, and it is for sure Q2. So quadrant 2. All right. Last up, we have -4, comma, pi over 6. So let's think about where that point lives. So this is pi over 6. All right. Now that's our angle, and our R value is negative. So that tells me not to measure the R value along the dotted line that I have as my terminal side of pi over 6. Instead, we want to go in the opposite direction. So we would be down here. This is for sure in quadrant 3. So when we find our rectangular point, we need to make sure it's a quadrant 3 point. All right. So x equals r cosine theta. So -4 times cosine of pi over 3. Nope. Put pi over 6, y'all. Pi over 6, please. Okay. So we have pi over 6. And at pi over 6, cosine is root 3 over 2. So we get -4 times positive root 3 over 2. Well, 2 goes into the -4, -2 times. So we get -2 root 3. That is our x coordinate. Okay. Now for y, we want r sine of theta, so -4 times sine of pi over 6. Well, sine of pi over 6 is 1/2, so we get -4 times a half, which is -2. So our ordered pair is -2 root 3, comma, -2. So from the origin, we go to the left and then we go down. That for sure puts us in quadrant 3. So this is our rectangular point, and it's definitely in Q3. Okay, so that is converting from polar to rectangular. Let's do two more, but let's make sure they're just like wacky. Okay, so just for the sake of fun, let's use our calculator. So get your calculators out. Example 4 says use a calculator to approximate the rectangular coordinates for each polar coordinate point. Now, you're going to start this the same exact way. Okay, we just have these wacky values. So like 3.6 radians is not like an exact value on a unit circle. 182 degrees is not an exact value on a unit circle. So we're gonna have to kind of eyeball these, and we're gonna end up rounding, but we'll get there. Okay, so for the first point, we have -3.1 comma 182 degrees. So let's figure out where this point lives. Okay. Well, if I were going to draw this angle, 182 degrees is barely, 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 barely in quadrant 3. Okay, it's 2 degrees past pi. Okay, 2 degrees past 180 degrees. Okay, so it's barely, barely, barely in quadrant 3. Okay, but R is negative. So that tells me that I don't want to plot my distance from the origin or from the pole in the direction of the terminal side of the angle. I want to plot it in the opposite direction. So we will go out 1, 2, 3.1. So this angle is actually in quadrant 1. Okay, barely in quadrant 1 because again, 182 degrees is barely in quadrant 3. Okay, so when we have that negative r, it scoots us over to quadrant 1. So keep that in mind. Now, x is equal to r cosine theta. So -3.1 times cosine of 182 degrees. We'll go to our calculator in just a second for that. And then y equals r sine of theta, which is -3.1 times sine of 182 degrees. Now, when we go to the calculator, make sure you're in degrees mode. Okay, so let's scoot to the calculator. I honestly don't know what mode. Oh, so I'm luckily in degrees mode, but remember, if you don't remember if you're in degrees mode and your calculator doesn't tell you, just go to mode and then you can see if you're in radians or degrees. I'm in degrees, so I'm good. So R was -3.1. So I want to type in -3.1 times cosine of 182. And we're going to round, let's do 1 decimal place. So we would get 3.1, okay? So the x coordinate of this ordered pair is going to be 3.1. And then to figure out what the y is, we do -3.1 times sine of 182 degrees. And we get if we round just 1 decimal place, we get 0.1. So we get 3.1 comma 0.1. So we get 3.1 and we get 0.1. So the ordered pair is 3.1 comma 0.1. And is this in quadrant 1? Yes, we have a positive x, a positive y. And if you think about this, we would go out 1, 2, 3, a teeny tiny bit more, and then we just slightly go above the x-axis. So that would be this point right here. This one up here is drawn a little dramatically. It should be more like way down here. So that does represent the same point, believe it or not. I'm going to go a little bit further out. All right. Now, for the next one, we're going to have to flip our computers, our calculators to radians. So we have 4 comma 3.6 radians. Well, let's think about 3.6 radians, okay? Because we're used to measuring radians in like units with pi. Okay. We know pi radians is equal to like 3.14 radians. Okay. So this is 0 radians. This is pi radians. This is pi over 2 radians. This is 3 pi over 2 radians. So where would 3.6 radians be? Well, just to make sure which quadrant we're in, we know that this is about 3.14 radians. Let's figure out what 3 pi divided by 2 is. So if I take 3, multiply it by pi, and then I divide it by 2, I get 4.7. So this is about 4.7 radians. This is about 3.1 radians. So 3.6 is going to be squarely somewhere in quadrant 3, okay? And we can safely say it's in quadrant 3 because our R value is positive. So when we measure out 3.6 radians and then we go 4 units along the terminal side, we're for sure in quadrant 3. So this is for sure a quadrant 3 point, okay? So with that said, x equals r times cosine theta. So 4 times cosine of 3.6 radians. Make sure when we put this in the calculator, you switch to radians mode. Y is equal to r sine theta, which is 4 sine of 3.6 radians. All right, let's go to the calculator and see what we get. So I need to first switch my calculator to radians mode. So I'm going to go to mode. I'm going to go down here until it's blinking on radians and hit enter, and it's going to switch it to radians mode. And second mode just takes me back to my home screen. So I want 4 cosine 3.6 radians. So if we round 1 decimal place, this is negative 3.6. And then I want 4 times sine of 3.6 radians. And that is negative, let's do 1.8. So negative 3.6, negative 1.8. So we get negative 3.6, negative 1.8, approximately. We did a lot of rounding there. So we get the ordered pair negative 3.6, comma negative 1.8. And the question is this for sure in quadrant 3? Yes, it is. So this is definitely in quadrant 3. This is our rectangular point. It's definitely rounded. It's an estimate. This is our rectangular point, for sure an estimate. But hopefully this makes sense, okay? So make sure you know how to take a point that's in polar form and convert it to rectangular form. In the next video, we'll flip-flop it. We'll take rectangular points and we'll convert them to polar points. You have to be a little bit more careful with that, all right?